Okay, so hi. Welcome to our talk. And today we're going to talk about microarchitecture attacks on RISC-V. And what is RISC-V? RISC-V is a new CPU architecture, and we are going to see how this architecture enables old and new attacks that lead to very powerful attack primitives. So how are we going to go through this talk? Well, first of all, we're going to recap CPU security basics, and we're going to learn what the state of the art in CPU security research in recent years was. And then we're going to learn about existing attacks. So we're going to see which attacks were possible in the past, and then we're going to transition with all of this knowledge to investigating CPU security on RISC-V CPUs. And well, who are we? We are both members of the RUTSEC research group at CISPR, a German research institution. And I'm Lukas Gerlach, a PhD student, and with me today is Daniel Weber.
And hi, I'm Daniel, and unfortunately not with us today is our supervisor, Michael Schwarz. And our entire research group focuses on CPU security. But one thing here, Lukas, what I still didn't quite get is, like, why do we even care? Why do we care about CPU security in the first place?
Well, let's start with a very easy to understand example, a live demo. And well, let's hope the demo gods are in our favor today. Maybe they are. And what we're going to see is a cache attack. And this cache attack is going to leak an interesting logo that you maybe already know. Well, and with this live demo, we've basically shown that it's possible to leak data to which you shouldn't have access to via a microarchitectural side channel.
And more precisely what's happening here is that we could just encode this data in the CPU component called the microarchitectural cache, and then we could just leak that later on. So the thing here is, once we saw something like this can happen and we can leak the placket logo, okay, that's fine. But is that really something we should care about? Because drawing a placket logo, that's way easier. But it turns out that CPU vulnerabilities can leak way more. So you can actually leak cryptographic keys, so directly private keys. But keys are not the only thing that we care about in today's security. We also care about browser cookies. And it turns out you can actually also leak browser cookies. It doesn't stop there. The thing is, you can leak almost arbitrary memory from your system.
Well, and now the question is, if we can leak almost arbitrary memory, from where can we leak it? What is the attacker model? And it shows that with CPU vulnerabilities, we can have a very high flexibility. So what we can, for example, do is we can leak data across the user space, kernel space boundary, which we shouldn't be able to do traditionally. And then we can also, to go with the theme from the browser, do attacks on the browser. So for example, fingerprint which websites a victim is visiting, or do attacks out of the browser. So for example, we can leak stuff outside of the browser sandbox from only the browser sandbox by using JavaScript. And even worse, if we're thinking about the cloud, we can also leak data from within virtual machines. So one virtual machine can attack another virtual machine or the hypervisor.
And it turns also out that this research field, especially those stronger attacks, is quite new. Like the story for those stronger types of attacks and where we actually started to really worry about CPU security started in 2018 with Meltdown Inspector. And I guess that most of you have already heard about Meltdown Inspector, but the fun thing here is that the story doesn't end there. Like recently afterwards, we found variants of such attacks, or more precisely, like CPU researchers across the world found more variants of those attacks, like MDS attacks. And it doesn't stop there either. Like even more variants came into play with LVI. And yesterday we saw power side channels during the Collide and Power talk. And it turns out that you can actually also abuse power side channels to leak information from your CPU. And then last year we figured out that you can actually go even further. Like CPU researchers from Schwarz figured out that you can actually abuse microarchitectural bugs. Like those are just implementation bugs now, because CPUs are so complex that you can just build bugs in there similar to software bugs. And you can just actually exploit that from within the software. Similar to what you saw yesterday, when you attended the Collide and Power talk, you saw that those power attacks can be even stronger. And we're still not at the edge there. Also for new CPUs, like the Apple chips, we also saw similar leakage, and even recently we saw attacks such as downfall or cache warp on Intel and AMD CPUs. And you can classify those attacks a little bit. You can say you have primitives to leak secrets, like Spectre, Meltdown, and MDS-style attacks. But you can also not only read stuff out of some victim's memory, but you can also change the data that the victim processes with. Like, for example, with Plundervault or Cache Warp, you can actually change those data. And so I think that CPU security is actually something we should care about. And all these things show how diverse that field actually is.
But Daniel, I mean, in the past, all these attacks you described are on Intel, or most of these attacks are on Intel and AMD CPUs, right? There's other architectures.
Yeah, fair enough. I have to admit that. Like, most of them were on Intel and AMD, but it doesn't stop there. Like, we also saw attacks on ARM. And on ARM, many things also work. Like, you have cache attacks there, and also some variants of Spectre and some variants of Meltdown. So that's not a thing, that's not a fault of AMD or Intel, but also ARM vendors have these same problems. So ARM, basically, you can say it's vulnerable to similar classes of attacks.
But wait, I mean, we don't have to stop at ARM, right? There's still other architectures. And one of these architectures is the topic of our talk. So RISC-V is a very new instruction set architecture that is great, not only because it's a very new and newly designed architecture, but also because it's fully open source in the standard. And you can actually get open source core designs even. So what that allows to is, for a similar method that we've done with open source software, you can basically do white box bug hunting. So you basically can, for the first time now, look at the source code of your chip and find bugs in the chip's source code. And, well, you can even go further. You can build your own hardware mitigations into this chip. You know what the chip does. You have the source code of the chip. So you can basically modify the hardware to be resilient against the kinds of attacks you want to prevent against. And this is exactly what academia has done a lot in the recent years, because, of course, academia wants to implement mitigations, and we want a nice, basically, stack to implement our mitigations on top on, and that has been RISC-V for the recent years.
Okay, but wait there. Like, academia, that's nice, and we're academics after all, but do we really care about academic things? Like Intel, AMD, ARM, we see these things, but RISC-V, is that just another academia thingy? Like, do we really care about that? Should we?
It turns out that you can actually buy RISC cores. So it's not only an academia thing after all. The first RISC cores are just coming up right now. And now we have available cores that we can actually buy in hardware. And this is the target of the rest of our talk. So basically what we analyzed are two different RISC-V cores that we've looked at and analyzed for microarchitectural attack surface. And these are namely the All-Winner D1, which is a core from China, and the Sci-5 U74, which is a core by Sci-5.
Okay, but is RISC-V actually going to be used?
Well, so let's look at it, right? Let's look at what the industry says. And we looked for it, and we found out that there's predictions that around 62 billion RISC cores are predicted to be running by 2025. So it seems that RISC is gaining quite a lot of traction. And even more, we have projects that support the entire RISC ecosystem with major vendor involvement, like Google, Qualcomm, and Samsung. And they actually try to bring RISC support into their products.
Okay, fair enough. Like, RISC-V is not an academic thing anymore, and it will be like one of the rising CPU vendors or CPU architectures out there. So let's ask the important question here. What about security? Like, what is the status quo on actual hardware implementations of RISC-V? And to analyze that, we wanted to start with a couple questions. Because one thing is, the very obvious thing, we have CPUs for quite a while now, and now we have a completely new architecture. Did we learn anything from a security standpoint? Are those CPUs now hardened against such vulnerabilities that we saw in the recent years? On the other hand, do academic mitigations, and we have a lot of them, do they actually make it into practice? Are they now implemented in our microarchitectures? Let's find out. And the other thing is, which I personally also found very interesting, like, does open source imply now better or worse security? Because for the first time ever, we're having an open source standard there. So what does it mean? And for that, we will analyze the C906 and the U74 CPUs, so actual hardware cores. But how do we do that, Lukas?
Well, I would say before we start jumping in right into the security analysis of these cores, we should understand how they work, right?
Oh,
and
good point.
So that basically means we should now very quickly understand how a CPU in general works. And basically, a CPU is just there to execute the instructions that you want to be executed and to do that as fast and reliably as possible. And to execute these instructions, you actually have to get them from somewhere, right? If you write a program that gets compiled somewhere, the instructions somehow have to end up where they get processed. And that's what we call the fetch phase, where we basically fetch an instruction from the processor's memory or from the memory of the system into the processor. After we end up with this instruction, we need to decide what we need to do to execute this instruction. This is the phase which is called decode, where we basically look at the instruction, parse it, put it into some internal representation, and then basically decide what are we going to do next. And after we decided what we need to do next, of course, we need to do that, right? And there's the actual phase where we execute the instruction. And this can, for example, be, if you look at something that you do arithmetically, as simple as an addition that you perform, right? This is where you actually do the work. And after you've done the work of computing, your instruction maybe needs to change something in memory for your program to have an effect, right? And this is what we do in a write-back phase, where we write the entire result back to the memory that we've used. So now we basically very roughly know what a CPU does. And now the question is, what kind of attacks are there and how do they relate to these different phases of an execution in the CPU? And so what we have is basically a lot of attacks that use timing in caches and predictors, which is a structure that is used to speed up memory loads and stores in the processor. And there in the recent years, we've seen really a lot of attacks, most notably flush and reload and prime and probe, which are two very generic primitives that allow you to leak metadata out of the cache. And they've really been applied to a lot of different contexts. We had a lot of attacks on cryptographic libraries with these primitives. More recently, we also had implementation bugs. For example, Daniel talked before about Epic Leak, where we could basically architecturally see something that went wrong in the microarchitecture, or Meltdown, where we can leak arbitrary data by a bug in the fault handling of the CPU. And then if you visit the Collide and Power talk, we also had a lot of attacks that abuse the physical properties of a CPU. So either this can be a rowhammer attack, which, for example, abuses how the DRAM stores memory and basically the nature of the DRAM itself to induce bit flips in the DRAM and bit powerful attacks, or it can be attacks on the power consumption of the CPU that allow you to infer what the CPU is doing by looking at its power consumption.
Okay, so that was quite a lot already, but let's actually just start to deep dive into our first attack. And the first attack that we want to discuss today is flush and reload. That's been a thing on x86 CPUs for quite a while now. So what's happening on RISC-V now? But to understand flush and reload, the cache attack, we first have to understand CPU caches a little bit. So let's suppose you have the following. On the right-hand side of the slide, you have your main memory, so your DRAM. In the middle, you have the CPU cache, and on the left-hand side, you have two lines of code doing memory accesses. And what's now happening? On the first memory access, we have a so-called cache miss. Because if you look at the CPU cache, it's just empty. So we call that a cache miss. That means we have to still fetch that data. And so we fetch that from the DRAM. And that takes actually quite a while. Because DRAMs, compared to everything else in the microarchitectures, are very, very slow. But after a while, this data comes back, and we can just forward that to the access. But it doesn't stop there. Like transparently, so without the programmer noticing, this data is also put into the CPU cache. And why is that nice? Well, the thing now is, if you have a second memory access, which accesses the same memory, well, then we can directly serve that from the cache. And we call that a cache hit. And the really nice thing is, our first access was really slow, because it had to travel all this way to the DRAM and back. And remember, the DRAM is very, very slow. Our second access, however, can just be directly served from the CPU cache. So it's really fast. And if I now equip one of you with a very high precision timer, you can actually plot that by just measuring those access timings. Then you see something like this. So yes, those are very small timings, but as you can see here, if your timer is precise enough, you can actually distinguish those two peaks. I would say quite easily. On the left-hand side, you have cache hits. On your right-hand side, you have cache misses. And that's a little bit of theory about CPU caches. So the one takeaway here is we can distinguish cache hits and cache misses, so we know whether something is in the cache or not if we access it. And once we have that, we can build our first attack there. So suppose you have two processes. Because we want to attack something, let's name them attacker and victim. And these two processes share some shared memory. And that's actually very common if you think about it. For example, all your shared libraries are named like that because they abuse shared memory for efficiency reasons. So we have just some library in there that both the attacker and the victim processes are using. And now suppose one of those two entities just does a memory access. Then the thing is, that data is now cached. So it's in the CPU cache now. And both actually see that cached memory. So once the attacker accesses that data, it's a really fast access because the victim has previously accessed that. And that's the idea of our first attack. So first, the attacker flushes this memory, or flushes the CPU cache. So hence the name flush and reload. And everything from the CPU cache is now gone, because flushing just removes the memory from the CPU cache. Now the attacker just waits, and at some point, the victim may access that memory. And if it does, well, then it's in the CPU cache again. We know how that works now. And the cool thing is now, if our attacker just tries to access this memory again, depending on that timing, we get the information of whether or not our victim has accessed that memory in the meantime. If they didn't, well, then we wouldn't see anything anything on there being parsed because it's uncached. But if they access it, well, then we just see that it's cached. So that's flush and reload.
I mean, yeah, and that sounds good, right? On RISC-V, we should also have shared libraries, right? Every system uses it. It's more of an operating system thing than it is a microarchitecture thing. But what we found out is that basically flush and reload does not work anymore, and we're gonna find out why that is. So typically, flush and reload is used to spy on control flow. So you have a victim that executes a branch that is secret dependent, and you want to infer that direction of the secret dependent branch. So you basically see which of the branches is cached, and then you find out which branch was basically executed by monitoring whether it was cached or not. And this requires shared caches for data and instructions, because when you perform this load, as Daniel illustrated before, this load basically hits both the data and the instruction cache. And on RISC, at least on the designs that we've analyzed, we have split data and instruction caches. So there's no shared element between data and instruction, which intuitively sounds very good for security, right? You don't want to share resources overly that you don't need to share. And this means that this cache design, at least for attacks that spy on control flow, mitigates flush and reload.
But wait there for a second. Like, okay, that's cool and all, so flush and reload is kind of mitigated, but let's not stop there. Like, negative results are okay, positive results are way better. And I'm really convinced that we can just do a short tweak there, and then everything will work again. And we called our new attack flush and fault, because it's a similar approach, but a little bit different. So the idea here is, let's try to spy on the branch of our victim. So depending on a secret bit, either A or B is executed here. And by executed, that also means that the memory of either A or B is fetched into the CPU cache. So if those are shared library functions, we can just measure that access timing. But because our data and instruction caches are split, we cannot do that directly. So we tweak our attack a little bit. First off, we start with the same thing. We just flush the memory. And it turns out on RISC-V, that's as easy as it has been on x86. There's just an instruction for that. It's sounding a little bit weird, but we just execute that and it works. The other thing is, instead of just accessing that memory, we jump to that memory. But we do not jump to A directly. we just jumped there misaligned. So if you ever played around with rob chains, for example, if you jump somewhere misaligned, chances are quite high that you crash. And we do exactly that. We just jump there and hope for a crash. And then we just handle that fault so that our attacker program does not abort. But the trick now is, for executing that code and for the CPU to figuring out that it should actually crash, it needs to fetch that code, either from DRAM or the CPU cache. So if we now take a look at the timing it took us to actually crash, we can still see whether the memory was cached or not. And with that simple variation, we can again mount cache attacks on RISC-V.
Well, that's cool. It sounded like this split cache would protect us here, but I mean, in the end, we see that with a little bit of creativity, an attacker can still bypass something like this, and this is in no way security mitigation, because it only prevents well-known cache attacks that rely basically on this load being shared in the cache, and does not prevent an attacker that tries to perform more sophisticated attack. So flush and reload, we basically fixed, but if we adapt our attacks to, for example, flush and fault, where we do not need this load, but rather execute directly and get the timing there, we can still mount attacks. And also on the other side, while we often want to recover control flow, there's also attacks that work with data accesses only. So you, for example, want to look at a secret, at an access pattern that is secret dependent in a library that does AES with optimizations. And so these attacks are also still possible.
Okay, but in the beginning, you mentioned way more attacks, like cache attacks. Okay, they work. But what about all these other attacks that we saw in the beginning?
Yeah, well, let's just step through how the CPU works. We basically had the fetch part now, and now we're looking at the part where we actually target the execution. And this execution relates to a concept in CPUs that is called a performance counter. And the performance counter is basically a tool that we build into our CPUs because CPUs become very, very complex, and it's very, very hard to reliably benchmark CPUs. So what we've done in the recent years is we increased the number of performance counters that ease benchmarking and really provide insight into the microarchitecture. So you're basically allowed to look a little bit into the actual implementation details of your processor by using these performance counters.
And what can you see there?
Well, for example, we can see such events as, for example, the cache misses. So we can see a lot of cache activity there, and you might already know how that relates to attacks, basically, because we've talked about cache attacks. You also see instructions that are executed or instructions that retire. And you also can monitor stuff like the CPU frequency, which you might again remember from the Collide and Power talk, where this was basically used to get an unprivileged interface into the power consumption of the CPU.
Like, okay, but that sounds quite nice. Like, benchmarking is cool, makes our code run faster. So where's the problem?
Well, so performance counters can themselves enable attacks, because if you think about it, we basically get an extra insight into what the CPU is doing that we didn't get before. And if these performance counters are shared, then by definition, they're also accessible to an attacker running on the same system. Think, for example, of a scenario where you're running in the cloud and sharing one CPU, or just a system that is shared between multiple users. So for example, if we go back to our example of inferring control flow, we have a branch here on the side. And this branch on the side basically depends on a secret, and we would like to know as the attacker, what is this secret? And to do that, we can look at the performance counters, and it turns out that some processors, for example, implement a branch taken event that just tells you whether the most recent branch was taken or was not taken. And this, of course, very trivially gives you the secret there, because you know whether the secret then is 1 or 0, right? And what is the fix, for example, in a cloud environment or a shared environment? Well, the fix is just to make the interface itself privileged. So don't give the attacker access to the performance counters, prevent it by putting the interface behind the wall of privilege.
Okay, so I'm starting to see a pattern here. Like, first we had timing for CPU caches, now we have debug interfaces or benchmarking interfaces. So similar pattern. So again, let's take a look what's happening on RISC-V. And once we took a look here, it was actually kind of interesting what we found. It turns out, if you just read the manual, or the standard to be more precise, some performance counters are just unprivileged, and not by some implementation choices, but it's dictated by the standard. And we think that's a really surprising thing, because we know that that's a security thing, and you can abuse that for attacks. And now a new standard comes along, gets standardized, and it's supposed to be unprivileged. It's not entirely hopeless, so some events are still privileged, and only a few unprivileged events exist. Like the attack on the previous slide using branch taking events, that does not work because they are privileged. But there are some leftovers dictated by this standard. And those two are the number of CPU cycles elapsed and the numbers of instructions that retire, so that finish execution. And if we have those two performance counters, it may not sound like too much, but it, again, gives us a few primitives that we can abuse to gain interesting information.
But Daniel, that sounds like a very limited primitive. Is there even an attack that we can do with that?
Of course. And to attack something, we, again, have to understand what do we attack. And this time, we want to circumvent a security mitigation called KSLR, Kernel Address Space Layout Randomization. And the idea is, if you have memory corruption exploits, like kernel exploits, to gain privilege escalation, well, then typically you require very precise knowledge of all these addresses. You really have to know where each function and each instruction is located in the kernel. So to defend against that, well, what can we do? We just randomize that location. We just take the kernel and move it somewhere else. And more precisely, the Linux kernel does that on every boot. So maybe we can just break this.
Well,
should work, I guess.
Let's find out, right? Let's get to our second live demo.
Okay, and so the idea here is, once you have such an interface again, and you can see debug mechanisms, then you can also just time, or then you can basically just read out the number of retired instructions. If you just do that and try to access all locations where the kernel can reside, then at some point you notice something strange. Because that's a peak. We actually see a peak at one location. And Lukas, where's the peak actually coming from?
Well, so this relates very closely to how the CPU works with memory and how the address translation in the CPU works. So if we have an address that needs to be translated in the CPU, we need to do a page table walk. And of course, we cannot access kernel addresses, right? That would be a security violation because we shouldn't access the memory of the kernel. So we have to abort there at some point. But it turns out the CPU can abort the page table walk much quicker if no page at all is mapped than if it has to check basically whether there's an access violation because we're accessing something in the kernel. And this is this timing difference that we see here. So first, there's nothing mapped before the kernel, so the time is basically very quick because we can directly abort the page table walk. And then as soon as we hit basically the first kernel offset, we see that the CPU has to check whether we are allowed to access, and it sees, well, there's a page mapped, but in the end I can't access that page because the page belongs to the kernel.
Okay, that makes sense. So as an attacker, basically then all I need to do is just take a look at this graph, just take the memory address, and then I directly know where our Linux kernel starts, and I can just continue with my normal memory corruption exploit. So it's nice.
Yeah, that's nice. And so what did we take away from this, right? So RISC-V, of course, have unprivileged performance counters, and this makes performance counter attacks possible again. So we saw a KSLR break. There's potentially more you can do. You can, for example, monitor activity in the kernel space with the user space counters. And in the end, it just shows again that there's an additional attack surface, and this attack surface potentially gets bigger when we add more performance counters or enable them for unprivileged users.
Okay, so basically cache attacks, they still work, a little bit of tricking around, but you get them to work. Same thing goes here. For performance counters, it's even weirder because the standard dictates unprivileged access there. But in the beginning, we mentioned even stronger attacks, like things like Spectre, for example. So let's take a look at what's up with Spectre. Does Spectre still work? Is that still a thing on RISC-V hardware? And to understand Spectre and to reason about that, we first have to understand branch prediction. So branch prediction is done by the branch prediction unit, in short, the BPU. And the thing is, if you execute code, branches are very expensive because they impact your execution speed. And if you take a look at the branch on the right-hand side and think about that a little while, then you're also trying to figure out where that's coming from. You may see a pattern here. And the problem is that the CPU tries to pipeline all instruction. So during the execution of instruction A, it already tries to execute instruction B. But once you encounter a branch, that's hard, because we do not know where to continue next. Is it A or is it B? No idea. We first have to evaluate the condition. So the CPU has to wait for such branches. And that's slow, because stalling our CPU and our entire pipeline, that takes a lot of time.
Well, Daniel, so why do we even wait? Can we not optimize that? We want our CPUs to be fast, right?
Yes, and it turns out we can, and that's the purpose of the branch prediction unit. So the idea is, okay, branches may be like, think of common branches like error conditions. They're probably always false, but only one time they're true. So if you think about it for a little while, you'll notice to see similar patterns. Like branches, they don't change their behavior every time they execute it. Typically, they stay similar. So we can just take a look at the history of a branch. So CPU vendors actually do that, and the branch prediction unit just keeps track of the history of this branch when it was executed the last few times. And then based on that information, it just predicts which branch direction is taken. Then it can just prefetch that memory into the CPU cache. So it's executed, or it's prefetched at least way faster. That's no execution yet, but it's at least faster.
Well, that's a really cool trick, and that probably optimizes our performance of our CPU in a very big way. But I mean, we are still having to wait at the branch.
Yes, good point. And the thing there is, what is still missing is so-called speculative execution. So why do we stop at predicting just the branch outcome and just prefetching that memory when we can even execute that memory? But doing that is a little bit more complicated because you have to differentiate two cases. In the first case, well, you have a correct prediction. That's easy. You just gained a lot of performance. And it's one of the key features why CPUs nowadays are that fast. But the problem is what happens if you predict falsely. And in a false prediction, you have to roll back the inner state of the CPU to the actual branch and then take on the correct branch. So that's a little weird, and some side effects occur there. Nothing that you can directly observe, but with a little bit of insights in the CPU, things can go wrong there.
Well, speculative execution, that sounds really close to that Spectre attack that you talked about earlier, right?
Yes, exactly. And that's also where the name Spectre comes from. But the thing there is, talking about Spectre on RISC-V, well, Spectre requires speculative execution because it's abusing those false predictions. But all tested RISC-V CPUs that were in our lab once we did those experiments, they do not have speculative execution yet. So that does not really work. Maybe on future CPUs, time will tell.
Well, but we still have this speculative prefetching. So we still basically have this thing where a branch is predicted and prefetched. And maybe that's exploitable as an attacker gadget, and it turns out it is. So using this prefetching, you can basically build a side channel on the instruction cache. And this side channel is really nice because we don't require shared memory, which limits us to attacking shared libraries, for example, only. And as a developer, you could just say, well, I don't use shared libraries. I only use static binaries, and then it's basically fixed. And it also has the cache line granularity, which is basically the best precision that you can get for such a cache side channel. Well, and how does that work? How can we basically go from speculative prefetching to a side channel? So what we have is, again, this victim on the right side that we want to, where we basically want to infer whether A or B was executed. And what we do again is we first flush the entire instruction cache with the fence instruction here. And after we did that, we basically, as an attacker, mistrain a prefetch gadget. So we basically make the prefetcher our friend and let it prefetch whatever we want. And we can prefetch almost arbitrary memory with that. And in this case, we decide to prefetch the beef branch. And now imagine that the A and the beef branch contain exactly the same function. So you couldn't distinguish them by timing normally, but I think you're seeing where this is going. Now one of the branches is cached and one of the branches is not cached. And as soon as you execute the victim, you're going to get a different time independent of whether the code in these branches is exactly the same. So what we've built now is basically a gadget that can infer control flow without relying on shared memory that we need to control and exploiting this speculative prefetching. So okay. We relied on this speculative prefetching.
Okay, but Lukas, one thing that crossed my mind there, like 2 weeks ago or so, we got this new RISC-V machine in our lab, right?
Right.
And we said like Spectre, that's not a thing because we have no speculative execution there yet. But doesn't this new chip, it has speculative execution, right?
I guess we should try, right? We should try. So what we did is we got this new CPU. We were quite unhappy that Spectre doesn't work on these CPUs, so it was quite interesting. And then we found this new CPU. And we thought, well, this CPU supports all the requirements for Spectre, so maybe Spectre should work on that. And actually, I think yesterday night, we implemented the Spectre exploit, which we can now also show in a live demo.
So and it turns out, once you have those more complex or more optimized RISC-V CPUs, well, similar things happen again. Like you again have speculative execution, and you can again leak strings from the memory. So in this case, we leaked the string Spectre on RISC-V hardware at Placket Europe 2023 from inaccessible memory. And to the best of our knowledge, that's actually the first demonstration of a Spectre attack on COTS hardware. So it was a little bit unsure whether it will work. Turns out it will just work.
And in the end, what we have now, different to the gadgets we showed before, is a gadget that allows you to read almost arbitrary memory given the right conditions. So this is different as it's basically the first transient execution attack on a RISC-V hardware CPU that allows you to leak much more than a side channel code.
Okay, and so the lesson that we take from that is BPU attacks, that's possible, and the limited speculation on some of those machines mitigate some well-known attacks. For example, Spectre. But the thing is, even with that limited speculation, you can do a lot of powerful things. But once you have more optimized CPUs, like the one that arrived in our lab 2 weeks ago, the problems come again. And we again have Spectre on RISC-V. So by that, we want to conclude for today and keep a little bit track of what we've seen on those machines. So for once, let's summarize that again. And we are under the impression that open source architectures are great. Yes, they have some limits there, but the thing is, for bug hunting, open source is great because you can actually take a look at the RTL level and actually search for bugs there. On the other hand, if you plan to mitigate attacks, you can just implement that. So if you have a hardware mitigation for an Intel or an AMD or an ARM CPU, implementing that is quite hard. For RISC-V, go ahead, just implement it. But what we also saw, and that's an unfortunate thing security-wise, is once you redesign a microarchitecture from scratch, it may sound great at first, but in the end, if you really want to optimize and want to become a competitor for most recent CPUs and for the big companies, you will end up with the same vulnerabilities as other architectures have. For example, cache attacks, that's a thing, prediction-based attacks, and even transient execution attacks like Spectre. And the thing is, if you're just redesigning something from scratch, it's also easy to make a mistake or at least some weird decision. So we had this one surprising design decision that unprivileged performance counters are a thing now again. And that's kind of weird. And if you actually want to play around with that code, and maybe you also want to buy your own core and want to test those experiments, or also you want to just read the code and how to mount such attacks, we encourage you to check out our GitHub repository in which we open source the code for all our experiments.
So what are the key takeaways that you should really take away from this talk? So first of all, we've seen RISC-V, and we've seen that it has a lot of potential. So there's a lot of adoption already. There's great projects on it out there. But on the other side, we've seen that redesigning something and making it open source, that does not fix all of the problems magically. So there's really a lot of requirements that go above basically making the stuff open source to get a secure chip. And if you build more complex processors, then you also end up with more vulnerabilities, as you've seen today. And this really means in the end that security research on RISC-V itself is really essential, and there really needs to be a lot of investment in security research to basically make sure that we have secure chips in the future.
And by that, we end our talk, and we are really happy to take on your questions. Thanks.
Thank you for your talk. I just have a question regarding, did you try your attacks on proprietary RTL using RISC-V? So for example, NVIDIA GPU contains a RISC-V core for doing a lot of stuff. Same for hard drives. They have also a RISC-V core for firmware. And more generally, like speculation attacks, side channel attacks are very interesting in the context of cloud computing. Hypervisor extension for RISC-V is not yet out, even though 2 days ago on the Linux kernel mailing list there is a DTB for a new CPU containing a hypervisor extension announced. What do you think about the ramification of those attacks?
So I think, so in general, in our work, we focused on CPUs that run a commodity system. So not on hard drive controllers, but more on complex CPUs. And they are just now coming out. And while some of the features, for example, the hypervisor extension, may not be implemented yet, I think it's a very good idea to start considering security very early in the design process. So you should not first build the hypervisor extension and then think about microarchitecture attack models. Instead, I think it's a really good idea to first look at the attack model and then think, how can we maneuver around that with basically designing our extensions.
Okay, so you said that flush and reload doesn't work because the instruction cache and data caches are separated. Does it also apply for the TLB, for the translation Lukas buffer, or are they also not shared?
So after all, it depends very much on the chip that you're using. So also this is a microarchitectural detail. So it's implemented on all the chips that we've seen now. But it doesn't mean that a new chip that is coming out needs to have these split caches. This is by no means a requirement of the RISC standard, and for the TLB, I imagine it to be the same. Some of them have now shared second-level TLBs, some of them don't.
So you didn't actually test this on the CPUs you have on hand?
I think we did TLB attacks on the CPUs. I would come back to you offline, and we can discuss in more detail which CPU doesn't and does share the TLB. I don't recall that right now.
Thank you.
Hi, thank you very much. I guess what I wanted to ask is, most of these come down to the laws of physics, kind of semiconductors and how they operate and how current flows. Where do you have any thoughts on how kind of changes in kind of semiconductor use or different substrates or different kind of how we measure these characteristics of these microprocessors might change to improve security?
So one thing I'm thinking when going into this direction is certain attacks actually require such properties like rowhammer, for example, where you abuse the characteristics of DRAM chips. So that's a very interesting attack scenario there. The thing is that's a little bit in the hand of the DRAM vendors. But for a lot of those attacks, you actually don't have to dive. You have to deep dive into how CPUs are implemented. But they're like a lot of those attacks are just not relying on the exact physical properties that you abuse there. Because like Spectre, for example, you just abuse how CPUs are, I'm saying on a high level, because it's a higher level than physical properties, are implemented. So you can a little bit think of the microarchitecture as just some software project. Like, yes, there are also bugs on the assembly level and maybe on the compiler level, but most of those attacks focus on the software code that is in there, so the actual firmware running on there. But those attacks definitely exist, but the research is still limited in the direction on how changes to RISC-V actually change that. So we'll see.
Hi. So compared to x86, where you only have a couple of lines of CPUs, with RISC-V, maybe we can have many types of different ones. Do you see that these microarchitectural attacks will be really reusable on all of these, or do you maybe expect that they will only apply to a couple of models?
I think that's in general a very, very double-edged sword, the point you're talking about. So we can basically have great flexibility, and I think that's also what many vendors find so attractive in RISC. But the thing is, so some of these attacks are going to transfer, some of them are not going to transfer, but the thing is, what you're going to end up with is you're going to have more small chips that do stuff differently, and that, in my opinion, increases the potential to basically make a mistake in the implementation. With x86, for example, we have 2 big vendors, and both of the chips are very well tested. If you're a smaller company, you probably can't afford to invest so much testing into the chip. So it's a very interesting thing that is also, I think, a big chance for RISC-V to develop, because we can have more specialized code. But I think on the microarchitecture level, it's going to show in the future whether that's helping or not.
All right, thank you.
No problem.
All right, if there are no further questions, then if you want to speak to us offline, we're happy to do that. Besides that, thanks for the interesting discussions.